mapping supermassive black holes in the distant universe. Astronomers have constructed the first map of the universe based on the positions of supermassive black holes, which reveals the large-scale structure of the universe. The map precisely measures the expansion history of the universe back to when the universe was less than 3 billion years old. It will help improve our understanding of dark energy, the unknown process that is causing the universe's expansion to speed up. The map was created by scientists from the Sloan Digital Sky Survey, an international collaboration including astronomers from the University of Portsmouth. As part of the SDSS Extended Baryon Oscillation Spectroscopic Survey, scientists measured the positions of quasars, extremely bright disks of matter swirling around supermassive black holes at the centers of distant galaxies. The light reaching us from these objects left at a time when the universe was between 3 and 7 billion years old, long before the Earth even existed. The map findings confirm the standard model of cosmology that researchers have built over the last 20 years. In this model, the universe follows the predictions of Einstein's general theory of relativity but includes components that, while we can measure their effects, we do not understand what is causing them. Along with the ordinary matter that makes up stars and galaxies, dark energy is the dominant component at the present time, and it has special properties that mean that it causes the expansion of the universe to speed up. Will Percival, professor of cosmology at the University of Portsmouth, who is the EBOS survey scientist, said, "Even though we understand how gravity works, we still do not understand everything. There is still the question of what exactly dark energy is. We would like to understand dark energy further. Not with alternative facts, but with the scientific truth, and surveys such as EBOS are helping us to build up our understanding of the universe." To make the map, scientists used the Sloan telescope to observe more than 147,000 quasars. These observations gave the team the quasars' distances, which they used to create a three-dimensional map of where the quasars are. But to use the map to understand the expansion history of the universe, astronomers had to go a step further and measure the imprint of sound waves, known as baryon acoustic oscillations, BAOs, traveling in the early universe. These sound waves traveled when the universe was much hotter and denser than the universe we see today. When the universe was 380,000 years old, conditions changed suddenly and the sound waves became frozen in place. These frozen waves are left imprinted in the three-dimensional structure of the universe we see today. Using the new map, the observed size of the BAO can be used as a standard ruler to measure distances in our universe. You have meters for small units of length, kilometers or miles for distances between cities, and we have the BAO for distances between galaxies and quasars in cosmology, explained Pauline Zarouk, a PhD student at the ERFU, SIA, University Paris, Saclay, who measured the distribution of the observed size of the BAO. The current results cover a range of times where they have never been observed before, measuring the conditions when the universe was only 3 to 7 billion years old, more than 2 billion years before the Earth formed. The EBOS experiment continues using the Sloan telescope, at Apache Point Observatory in New Mexico, USA, observing more quasars and nearer galaxies, increasing the size of the map produced. After it is complete, a new generation of sky surveys will begin, including the Dark Energy Spectroscopic Instrument, DSI, and the European Space Agency Euclid satellite mission. These will increase the fidelity of the maps by a factor of 10 compared with EBOS, revealing the universe and dark energy in unprecedented detail.